Hey everyone, welcome to This Explainer. Today, we're unpacking something absolutely crucial: how deep learning is completely revolutionizing the way we analyze medical images. Pretty much as soon as it became possible to load medical scans into a computer, researchers were already dreaming up systems to automatically analyze them. But the methods we use to process these vital images, they've undergone a massive fundamental transformation over the last few decades. So today, let's look under the hood together at the algorithms that are quite literally learning to see the human body.
Okay, so here's our roadmap for today. We'll start with the deep learning shift, look at the architectures behind it, jump into classification and detection, explore the power of segmentation, and finally wrap up with registration and enhancement. Let's get right into it.
Part 1. The Deep Learning Shift. Let's get a little historical perspective. It's honestly kind of wild to look back at the AI timeline. I mean, we literally started with these super rigid expert systems back in the 1970s. Back then, image analysis relied on sequential pixel processing, stuff like edge detectors, line detectors, and mathematical modeling just to fit circles and ellipses. These were compound, rule-based systems, often called GUFI, or good old-fashioned artificial intelligence. And honestly, they were brittle. By the 1990s, we shifted over to supervised machine learning, using training data and statistical classifiers. But the real watershed moment, the game changer, happened in December 2012. That's when a convolutional neural network called AlexNet completely crushed the ImageNet competition, proving once and for all that deep, multi-layered models could outperform anything we had ever built before.
So, what's the real takeaway here? It's the massive shift from human-crafted, honestly pretty brittle if-then rules to modern deep learning. Back in the 90s and 2000s, the bottleneck was always feature extraction. Human researchers literally had to sit down and manually design the mathematical rules to extract what they thought were the most discriminant features from an image. Deep learning flips this entirely on its head. Instead of a human deciding what a tumor looks like mathematically, the computer actually learns the optimal features itself, directly from the raw data. It learns increasingly higher-level representations through its many layers. And this isn't just some technical upgrade. It means the AI can catch subtle disease markers that a human eye or a human-written rule might completely miss.
Moving on to Part 2. The architectures behind it. Basically, the actual brains of the AI. When you map out these artificial brains, the structural differences are just fascinating. On one end of the spectrum, you've got simple autoencoders that basically try to find hidden structures by compressing and then reconstructing data. And then on the other end, you have these incredibly complex, multi-stream convolutional neural networks that are tailored for highly specific visual tasks. Each of these architectures is uniquely wired to process visual information in a completely different way. You can really think of the convolutional neural network, the CNN, as the visual cortex of our AI. The absolute brilliance of a CNN lies in its shared weights. It processes patches of an image using convolution filters to detect patterns, like an edge or a specific texture, without needing a separate detector for every single possible location on the scan. It doesn't matter if that lesion is hiding in the top left or the bottom right, the CNN is translation invariant. Combined with pooling layers that aggregate pixel values to look at broader and broader contexts, CNNs dramatically reduce the number of parameters the system needs to learn while vastly improving its visual understanding.
Now, this massive explosion of research and application in medical imaging, it definitely hasn't happened in a vacuum. It's been completely supercharged by these accessible, open-source GPU computing libraries. We're talking about packages like Caffe, TensorFlow, Theano, and Torch. They provide incredibly efficient implementations of all those complex mathematical operations, like the convolutions we just talked about. And because of this, medical researchers can actually focus on high-level architectural design and solving real clinical problems, rather than wasting their time coding low-level math for graphics processing units.
All right, Part 3, Classification and Detection. It's all about finding the needle in the haystack. So here's a very real problem we face. Medical datasets are often tiny. We're talking maybe hundreds or thousands of exams, which is nothing compared to the millions of natural images used in general computer vision. To bypass this, researchers use transfer learning through two distinct strategies. Basically, you take a network that has already learned how to see by looking at millions of everyday photos. Then you either use it strictly as a feature extractor, plugging its outputs into a traditional classifier, or you fine-tune its deeper layers specifically on your new medical data. It's actually incredible when you think about it. An AI originally trained to recognize everyday objects like cars and cats can be fine-tuned to spot tumors with near-human expert accuracy. When an AI is hunting for a tiny abnormality, context is quite literally everything. You can't just stare at a few pixels in a vacuum. That's why multi-stream architectures are such a game changer. They process both the local lesion appearance, those really high-resolution details, and the global contextual location simultaneously. Sometimes they do this by feeding the network patches at different scales, or by using 2.5D approaches where multiple orthogonal slices of a 3D MRI or CT scan are fed into separate streams. This is exactly what allows the network to accurately spot abnormalities across incredibly varied and complex scan types.
But there is a massive, massive challenge in all of this, and it's called class imbalance. Think about it. The vast majority of a medical scan, like 98% of it, is perfectly healthy tissue. So when an AI is classifying every single pixel to detect a lesion, it's essentially looking for a needle in a haystack. The system gets flooded with millions of easy-to-discriminate healthy pixels, which can actually prevent the network from focusing its learning on the challenging, suspicious areas. To fix this, researchers have to use clever tricks, like selective data sampling, where the wrongly classified samples are fed back into the network more often. It basically forces the AI to focus on the hardest parts of the image.
Which brings us to part 4, the power of segmentation. Let's talk about mapping boundaries. Historically, if you wanted to segment an image, you'd use this sliding window approach, evaluating the same patches over and over again. Super inefficient, right? It creates massive redundant calculations. To do this efficiently today, we use fully convolutional networks, or FCNNs. By rewriting the fully connected layers as convolutions, an FCNN can take an entire input image and spit out a full likelihood map in just one pass. Taking this a step further, you have the U-Net architecture, which acts kind of like digital tracing paper. It uses a contractive downsampling path to grasp the overall context, and then an expansive upsampling path to precisely localize the boundaries.
And it turns out the real magic, the secret sauce of the U-Net, is in what we call skip connections. See, as the network compresses the image down to understand the global context, it loses those tiny, fine spatial details. Skip connections literally bridge that gap. They take the high-resolution local details from the early layers and seamlessly merge them directly with the global contextual picture in the later layers. This lets the network generate an incredibly accurate, full-resolution segmentation map in a single forward pass. It's honestly a remarkably elegant solution to a really complex spatial problem. Finally, Part 5, Registration and Enhancement, how we align and improve these scans.
Okay, so when tracking a patient's progress over multiple visits, doctors have to perfectly overlay today's scan with last month's scan. We call this spatial alignment, or registration. AI is attacking this with 2 rapidly evolving approaches. The first uses deep networks to estimate a local similarity cost between 2 images, which then drives a traditional iterative optimization algorithm. But the second approach? That's where it gets really futuristic. It uses deep regression networks to directly predict the mathematical transformation parameters, the exact spatial shift required in one shot. In one study looking at brain MRIs, this direct prediction method achieved visually similar alignments, but with a staggering 1,500 times speedup compared to traditional methods. That is an absolute game changer for hospital workflows.
But beyond just aligning things, we are fully entering the era of image generation. These multi-stream networks can actually take one or more low-resolution inputs and generate stunning, high-resolution super images. And it gets crazier. Imagine a scenario where a patient simply can't undergo a specific type of scan. Deep learning architectures can now be trained to infer completely missing spatial information, like literally generating a simulated PET scan entirely from an MRI. This means less radiation exposure and fewer trips to the scanner for patients, all thanks to predictive AI. Plus, these generated images can be used to ensure computer-aided diagnosis systems don't just fail when physical data happens to be missing. Leaving you with that thought, I really hope this explainer has eliminated the incredible anatomy of medical AI for you. We've journeyed all the way from those rigid, rule-based systems to the highly elegant, self-learning architectures like CNNs and U-Nets. We've seen how they combat the challenge of class imbalance to detect the tiniest lesions, and how they map complex boundaries with profound precision. As these networks move beyond just analyzing data to actually generating and enhancing it, it begs the ultimate question. As generative models continue to synthesize missing data and predict detailed alignments, how soon will deep learning completely rewrite the everyday workflow of patient diagnosis and care? It's a fascinating future, and it's unfolding right now. Thanks for joining me on this explainer. I'll catch you next time.